All right, hi everyone. Welcome to the BHI Colloquium. Today is our pleasure to have Scott Collier. Scott is a senior postdoctoral associate at the MIT Center for Theoretical Physics, and previously was a center fellow at the Princeton Center for Theoretical Scientists after completing his PhD at Harvard in 2020. Is broadly interested in non-perturbative aspects of quantum field theory and quantum gravity, and his recent work has focused on the role of space-time wormholes, disorder averaging, and quantum chaos in holographic dualities. And it's our pleasure to have him here today.
Great. Well, thanks very much for the introduction. I'm very glad to be back in Cambridge. I'm at MIT for the next few years, so looking forward to chatting with everyone. Very happy also to be back at Harvard in particular. So today I'll be telling you about mostly about this project that appeared a few months ago, and I'll mention some work in progress together with Lorenz Eberhardt, who's now at the University of Amsterdam, and Mengyang Zhang, who's a grad student at Princeton. So let's get started. There we go. Okay, so this is a talk about quantum gravity. Of course, you know, it really important goal in theoretical physics is to understand the quantum mechanical nature of gravity. This is important and interesting for a wide variety of reasons that I'm sure most of us here understand. But often it's not really clear what this would even mean. And one concrete starting point that the literature has focused a lot on, particularly in recent years, is the so-called Euclidean gravitational path integral. Now, so in gravity, we specify boundary conditions. I call these partial M. And we integrate the gravitational action over a fluctuating metric. We gauge diffeomorphisms, and then finally we sum over topologies. And the main thing I want to emphasize here is that this is a very schematic equation. And in most situations, the rules that govern this computation are totally unclear and essentially made up ad hoc. Some of those questions that one might be worried about include, like, you know, what topologies should we include? Do we want to allow singularities? When is the saddle point approximation to this sum valid? How do we go beyond the saddle point approximation? What about off-shell configurations, which are not even solutions of gravity? Now, for the past 30 years, one of our main handles on quantum gravity has come from the holographic principle, which of course recasts quantum gravity entirely in terms of a specific, ordinary, non-gravitating quantum system that lives on the boundary of space-time. And in this setting, the gravitational path integral amounts to the partition function of the boundary quantum system. And as I'm sure most of you have heard of in many talks, the ADS-CFT correspondence, where the bulk is some negatively curved space-time and has some conformal field theory living on the boundary, furnishes the most famous and, importantly, the most explicit realizations of holography. And most of these explicit realizations, in fact, involve string theory constructions. And for the point of view of understanding this mystical object, the gravitational path integral, the main thing I want to emphasize here is that string theory is not very well understood non-perturbatively. So these questions of summing over topologies, in principle, involve non-perturbative effects in string theory. And typically, we just formulate string theory in a very background-dependent way, you know, studying some fluctuations around some background that we choose. And moreover, the constructions involve many perhaps unfamiliar and one might hope inessential ingredients like supersymmetry and debrains. It's not totally clear how necessary these ingredients are. And in practice, in view of this first puzzle, we in fact often view the boundary dual, the boundary quantum system that lives on the boundary, as in fact providing the non-perturbative definition of the bulk theory. So one might hope, and this may be naive, but one might hope that it would be possible to retreat somewhat from string theory. In particular, you might wonder whether it's possible to isolate the essential physics and consistently formulate a more simple theory of gravity, maybe something like pure quantum gravity. In this case, the boundary quantum system would describe the physics of black hole microstates and gravitons holographically. So if one could make this precise, it would be very exciting because it would provide a very clean theoretical laboratory where you could study very basic questions in quantum gravity and quantum aspects of black holes. Now, there's good reason for skepticism about this program. I think that's totally fair. But even if it's not possible to do totally consistently, we might learn something along the way about what the minimal set of ingredients needed for a consistent formulation of quantum gravity are. And in fact, if you really believe that string theory is the only game in town, you might optimistically hope to be able to prove that. Understanding these simpler theories of quantum gravity may in fact lead you to a newer or a somewhat modified notion of the holographic principle for these simple bulk theories, where instead of having some specific quantum system on the boundary, there's a more mesoscopic description in terms of that captures the statistics of the space of UV completions. Now, indeed, over the past 5 or so years, there's been a lot of interest in a two-dimensional theory of quantum gravity, which is almost pure gravity. The most famous example is Jakiv-Teitelbaum gravity, which is a theory of two-dimensional quantum gravity coupled to a dilaton, that's this field capital phi, and deformations thereof. So this is a theory with a sort of non-standard Einstein-Hilbert term. You see that there's phi times r instead of just r that appears here. And the reason this theory is so simple is because you can just integrate out phi. And so this ends up setting, it fixes the curvature to be r equals -2, which means you're looking at hyperbolic surfaces in the bulk. And this theory is not entirely some toy theory that we like for its own sake. It does actually arise universally in the near extremal limit of higher dimensional black holes. And indeed, supersymmetric versions of this theory have recently facilitated precise counts of higher dimensional black hole microstates. Yes, indeed.
But there's no example in which this arises as decoupling, right?
That's right.
It's always this coupling.
That's right. That's totally fair. But nevertheless, it has still facilitated these more recent black hole microstate counting, reproducing of indices.
Do you remind us why you need negative scale expansion?
Well,
Choice?
this is a choice. Yeah, this is a choice. It turns out to be a nice theory because 2D hyperbolic manifolds are very well understood.
What do you mean facilitated microstate funding? You don't get microstate funding from that theory.
You can reproduce protected quantities from the theory, so like certain supersymmetric indices, and you can even reproduce the fact you can even reproduce the integer that you get in these index computations, despite the fact that you're doing gravitational path integral calculation, using the fact that this theory arises in this near extremal.
But you could say the same thing about just Euclidean four-dimensional quantum gravity.
Can you actually do microstate counting from?
That's what gives it on that, right? Facilitated.
It's a more coarse. I think the people who did these works would probably argue that that's a more coarse-grained observable than these indices.
But surely we can't see the microstate from that edge.
That's fair. That's fair.
That theory can nearly be solved, right, by going to the point.
Yeah, that's right.
And there's no microstates there.
Not in the sense that people normally mean when they say microstate counting. That's true.
Well, what other sense is there?
I just mean like these computations that have reproduced the integer index. I think.
But would you agree that if we take this theory, we quantize it, we count microstates, we don't get the semi-classical entropy of the black hole?
Yeah, that's probably right.
So wouldn't that be evidence that this is not a good theory?
On its own, probably not. No. I mean, probably yes. I agree. On its own.
And maybe the second point is further corroboration of that view.
Yeah, absolutely. Yeah. Yeah, exactly. So the point Andy was anticipating was that part of the reason for the recent surge of interest in this model, not the entire reason by any means, is recent work that showed that the holographic dual of this theory is in fact a double-scaled random matrix integral. So this is an ensemble of boundary Hamiltonians rather than a particular quantum system on the boundary. And this was shown in this sort of landmark paper by Saj, Shanker, and Stanford in 2019. Okay, so let's go up in dimensions. So perhaps the next simplest theory of gravity that one could imagine considering is three-dimensional Einstein gravity with negative cosmological constant. And this is what I'll be talking about for the most part today. And you can imagine even coupling this theory to some massive point particles. So here you have the usual Einstein-Hilbert term with a negative cosmological constant, and you have the Gibbons-Hawking-York boundary term. Now, at first glance, this theory is completely trivial and not interesting to study. The reason for that is that all solutions are locally identical. They can all be viewed as quotients of hyperbolic 3 space by some discrete group. So locally, the gravitational dynamics is totally not interesting. And indeed, there are no propagating gravitational degrees of freedom to the bulk. So no gravitational waves in this theory. But it's not totally trivial. And the reason for that is the presence of the asymptotic boundary, which hosts a rich structure of boundary gravitational dynamics. You can think of these boundary gravitational dynamics as analogous, as gravitational analogs of the edge states of some quantum Hall system. And in fact, these gravitational edge modes furnish an infinite dimensional asymptotic symmetry algebra, which is in fact the Virasoro algebra of conformal symmetry in 2 dimensions. And this indicates the presence of some boundary 2D CFT with a central charge fixed in terms of the ADS length L and the Newton's constant G as follows. But most importantly, this theory has black hole solutions. And that's the main reason for our interest in this model. So what would it mean to solve this theory, even in principle? The conventional wisdom until a few years ago was that, well, one should construct the dual 2D conformal field theory that was anticipated by this observation of Brown and Hinot, like 40 years ago almost. And in particular, you should, in fact, construct a family of 2D conformal field theories that admits a large central charge limit so that the theory becomes semi-classical. Now, what does it mean to construct the conformal field theory? Well, the CFT is completely solved in terms of 2 infinite ingredients. The first is the spectrum of local operators of the theory. So these are operators which are labeled by 2 quantum numbers, h and h bar. Those are the conformal weights that tell you how they transform under conformal transformations. And finally, there's also their dynamics. So they're 3-point functions or structure constants. That's like the entire dynamical content of the theory. And so what would the spectrum of a theory, the dual of something like pure 3D gravity look like? Here's a cartoon of the spectrum. So here at h bar equals 0, you have empty ADS3. This is just the identity operator in the dual CFT. The CFT has some discrete spectrum, and in the semi-classical limit, you expect some huge gap until you hit this C/12 threshold. This is where these states can start being interpreted as black hole microstates. And this spectrum, in fact, becomes exponentially dense because the entropy here is very large. And the dynamics of these states are expected to be, in a rather precise sense, chaotic. And the question the CFT literature has asked over the past few years is whether this kind of very naive spectrum is even consistent with basic CFT axioms, because CFTs are extremely rigid theoretical structures, highly constrained by symmetry. And despite a lot of work that has been done over the past several years to carve out the space of possibilities in theory space, nothing even close to this kind of spectrum has been constructed. But I want to emphasize that it hasn't been ruled out either. So part of it could just be a lamppost principle. It's just very hard. Yeah.
I'm not sure what you're saying. Aren't the usual stringy ones examples of CFTs?
Those have lots of low-lying degrees of freedom. They don't look anything like pure gravity.
Oh, I see.
Yeah.
Oh, where did you, I see.
Here, there's a big gap between this empty ADS3 and this black hole threshold.
Okay.
Yeah. At the very least, you might expect a very sparse light spectrum to facilitate some extended regime of validity of the Bekenstein-Hawking formula.
Sorry, when constructing this kind of pure gravity, like, are you including conical defects in this theory, or like?
One could imagine augmenting, having some sparse set of low-lying operators. I don't think that would really, especially if the dimensions of those operators scale with C to any low-energy observer, in the semi-classical theory, they would only see boundary gravitons. So it would, to that observer, look like a pure theory. So I would also be happy with that. But there's no example of a theory with a parametrically large gap at large central charge. So you could even imagine loosening this this precise threshold. So now there are hints of what this theory might look like from the low energy effective theory. And the simplest example to state is provided by the Bekenstein-Hawking entropy formula, which states that the black hole entropy is given by its area over 4G nu. Now, as Andy mentioned earlier, this entropy can be computed in the low energy effective theory from the contribution to the gravitational path integral from the Euclidean black hole saddle. And so the way to interpret this is as a hint from the low energy effective theory about some coarse-grained statistical properties of the microscopic UV completion. And indeed, we interpret this black hole entropy as encoding the coarse-grained density of states, which is indeed what tells us that the spectrum in this black hole region here is very dense. Now, in addition to these Euclidean black holes, ADS3 gravity also admits multi-boundary Euclidean wormholes. And the one thing I really want to emphasize here is that these are bona fide genuine solutions of Einstein's equations. So these are solutions with two asymptotic boundaries. Here I've called it sigma. You can imagine it's some Riemann surface or a torus. And you can even write down in some special cases the exact metric for this Euclidean wormhole configuration. Here d sigma is the hyperbolic metric on sigma. And these pose a puzzle for the usual holographic paradigm because these give non-factorizing contributions to the gravity path integral with multiple boundaries. And this is naively inconsistent with the quantum gravity theory as having a single boundary quantum system. And this problem has been referred to as the factorization problem. So if the boundary theory is some dual CFT, when you compute the path integral with multiple boundaries, you expect it to factorize into the product of the partition functions of the CFT. And these contributions manifestly do not factorize.
Why do you expect it to factorize?
If the boundary theory is a single quantum system, then when you sum over topologies and do all the gravitational path integral magic at the end of the day, because the path integral only depends on the boundary, it should factorize into the product of partition functions of the CFT.
So they shouldn't interact.
After summing over everything in the gravitational path integral, there might be some very Baroque cancellation mechanism, but this mechanism is still poorly understood.
What is the status of the proposal? I think it was Collier, I guess, and that these things compute sort of expectation value of rho squared minus
in some coarse-grained sense.
Expectation value of rho wall squared.
Yeah. So that's a particular case here. It's actually that example is actually not a solution. It's an off-shell configuration in 3D gravity, but I think the interpretation is robust.
You think that interpretation?
At least in the space, the statistics that are captured by that variance of the density of states is it encodes the universal level statistics that one would expect of a quantum chaotic system, which one believes that the CFT is dual to ADS3 gravity.
This is a different kind of geometry, and
this is kind of different. Yeah,
there's no interpretation of this.
I'll tell you some interpretation in a second. Yeah, it's morally similar. So the point of view I want to argue for is that one should view these Euclidean wormholes as providing a low energy window into the UV microscopic completion of the theory in exactly the same sense as the black hole entropy. So we interpret these multi-boundary Euclidean wormhole solutions as telling us about coarse-grained statistical properties of the CFT data. It's ignorant of some UV details of the theory, in a sense averages over that non-universal UV physics. So here's an example of a Euclidean wormhole that has two sphere boundaries. Here I've coupled the theory to matter. So the boundaries are actually three punctured spheres, and you have these three defects traversing through the bulk of the wormhole. And recall I told you the structure constants of the CFT are like the 3-point functions on the sphere. So we interpret this kind of two boundary configuration as contributing to the variance of the CFT data of these OP coefficients or structure constants squared. So that's how we interpret these things. More provocatively, one might try to take it a step further and try to interpret these Euclidean wormholes as computing averaged CFT quantities in some putative ensemble of chaotic holographic duals. But the status of this is very much up in the air. And indeed, one can formulate a random ansatz for this CFT data that we think of as some Virasoro version of the eigenstate thermalization hypothesis. So you consider a theory where the structure constants,Cijk, are given by the square root of the variance times some random tensor with Gaussian statistics. So you can compute average CFT quantities, products of CFT quantities averaged in this Gaussian ensemble. And in fact, you can show that these average CFT quantities, in fact, reproduce gravitational on-shell actions, and in some cases, also one-loop effects in the semi-classical theory. So here's the interpretation of this wormhole I drew at the beginning with two asymptotic genus 2 boundaries. You compute the on-shell action, and you can show that this is given by the average product of CFT partition functions in this Gaussian ensemble that I defined down here.
Wait, how do you show that if you don't know what the CFT is?
That's the thing. You can compute CFT observables by doing a conformal block decomposition, which is where the CFT data enters, and then applying this Gaussian ansatz. So any given draw from this ensemble is surely in this swampland. It's not actually a CFT, but you can still compute average quantities in this ensemble because all you need to know to solve the theory are the structure constants.
What about gravity itself?
A priori, nothing. It's a kind of silly guess that you can start with, and will turn out not to be fully consistent on its own. Like gravity will require non-Gaussian contributions, but at the level of the on-shell action, it's sufficient. Like at the level of the saddle point action, it's sufficient to reproduce gravity actions. But as I alluded to earlier, this really cannot be the full story. And here, there's a really important difference in higher dimensions from this JT random matrix duality, which is that when the boundary theory is a field theory, especially a conformal field theory, there are an infinite set of constraints from locality of the boundary theory. These sometimes go under the name of crossing symmetry or modular invariance. And so for that reason, unlike in random matrix theory, not just anything goes. And you can't do the averaging in an arbitrary way. So this Gaussian ensemble satisfies these constraints on average, but higher moments of the constraint equations do not vanish. And indeed, there can be large violations of these consistency conditions, as was recently emphasized in a paper by Dan Jeffress and collaborators. And more conceptually, in the absence of something like a conformal manifold, it's not even clear in principle how you would go about defining an ensemble of chaotic CFTs, which are believed to be isolated solutions to these equations, or random CFT, how that should be formulated. So there's still a lot to understand here.
In the usual holographic response, this notion of averaging never comes up.
Yeah.
So how did you guys motivate?
Well, we were curious about the interpretation of these Euclidean wormhole saddles, which in 3D gravity, in fact, even unlike 2D, in 2D, most of these Euclidean wormholes are not actually saddles. In 3D gravity, this factorization somehow even starker because these non-factorizing contributions to the path integral are actually solutions of Einstein's equations. So it feels that they should be included.
Yeah.
We don't have a mechanism to exclude them, that it isn't ad hoc.
So the averaging is summing over these Euclidean wormholes in bulk.
It's an interpretation of the contribution of these wormholes. But I don't want to give the impression that averaging is some fundamental thing. I think it's some artifact of doing these simple calculations at the level of individual saddles.
So, but what's the ultimate hope that you'll be able to understand where the averaging comes from?
That will explicitly be able to understand the averaging as some sort of coarse graining over the microscopic UV data. Yeah, there was a question.
Sorry, in this gravitational theory, do you allow the existence of defects?
Yeah. So you can augment this theory to include, so for example, this kind of contribution where you have these defects threading the wormhole. You can modify the theory to allow massive point particles.
Like,
They just need to be heavy enough that they back react on the geometry to source some conical defect, and then you can treat them in the action with some world line action.
like does that even matter in the last result?
Sorry?
I mean, like, whether you include defects or not, like, does it matter when you get this result?
Yeah, no, this would still, in the semi-classical limit, this would still give the dominant contribution.
This makes sense for a single CFT, right? You don't have to have a pair.
Well, it does in principle, but you have to tell me what the bar means. You have to tell me what the coarse graining procedure is for it to make sense in a single CFT.
I mean, I guess what we'd like, I don't like the ensemble averages.
Yeah, that's totally fair.
It's not unitary. The whole point was to make something unitary, and if we're throwing that away, what's left?
Yeah.
But you'd like to pull these two pieces apart, right? This is a different kind of average. It's averaging over 3.5.
One would
That
ultimately,
makes a lot of sense.
yeah.
You might hope, I guess, there's super selection sectors like in the old wormhole story, but somehow nobody's been able to make that.
Not really, no. Yeah, all I wanted to say here is that I think you totally can interpret these wormholes in a given theory, and there has been some recent work in that direction, but you need to specify the coarse graining procedure just to make quantitative sense of the formula. Okay, so the point of that whole discussion was to motivate trying to make sense of the bulk theory in its own right, because the boundary theory is confusing. So yeah, the upshot is that the dual of this pure ADS3 gravity, or maybe coupled to matter theory, is highly unresolved and in flux. And so, although not trivial, as I tried to emphasize earlier, the bulk does behave in many ways like a topological theory, in the sense that all of the dynamics are localized at the boundary. And so we'll see that topological quantum field theory will provide the natural framework for us to exactly formulate the theory. So today, in the remainder of the talk, I'll discuss the canonical quantization of the theory, and we'll concretely relate it to a novel but well-defined TQFT, which we called Virasoro TQFT. And the main thing I want you to take away from this talk is that this is not just formal, it's quite explicit and very useful. And I'll argue that it leads to essentially a complete solution of 3D gravity, at least at the level of fixed on-shell topologies. So we'll completely solve the theory at the level of these individual topologies, but the puzzles I mentioned at the beginning, having to do with the sum over topologies and dealing with off-shell configurations in the path integral, those will still remain.
If you fix the topologies, you still have background independence, right?
Yeah.
So the pure theory has an anomaly in large diffeomorphisms. How is that consistent with
Do you mean?
the modular transformation?
Well, you would want to formulate the theory in a way that it does not have an anomaly. That would require dealing with with the sum over topologies.
Or just the force, or you're saying it's.
Well, there is you can write down modular invariant partition functions, in fact, that have this property of the large gap, but they have some other topologies, like the fact that the spectrum is continuous rather than some discrete sum, which has recently been reinterpreted in its ensemble sense. But more importantly, there's some unitarity issues. But modular invariance in principle, we can deal with by summing over topologies. I'll give a concrete prescription at the end for how to deal with that. Okay, so here's the plan for the remaining half of the talk. I'll start by discussing the phase space of this 3D gravity theory, and then I'll proceed to quantize the phase space, and this will lead us to this Virasoro TQFT. And I'll conclude by describing the prescription to compute partition functions in 3D gravity. I'll lay out the general procedure, and if there's time, we'll give some explicit examples. Okay, so the starting point for this discussion of the phase space is the observation that ADS3 gravity in the first order formalism famously admits a reformulation in terms of SL2R Chern-Simons theory. And the reason for that, so in the first order formalism, the gravitational variables are the Vielbein and the spin connection. And from this gravitational data, you can form two SL2R gauge fields, A and A bar. And the reason I call these SL2R gauge fields is because they transform like SL2R gauge fields under infinitesimal diffeomorphisms and local Lorentz transformations in these gravitational variables.
So what's the signature again?
Signature is Lorentzian.
Oh, it's Lorentzian.
Lorentzian for now.
Okay.
Yeah, because I want to do canonical quantization. So I want to like pick some initial value surface, figure out the phase space, and then quantize. But I will then swiftly proceed to, once we figure out what the Hilbert space is, I will proceed to Euclidean signature.
But it still remains an SL2R.
Yeah,
That's
right. Yeah. Okay, so yeah, and indeed, the Einstein equations in these variables tells you that A and A bar are flat connections, and you can write the Einstein-Hilbert term in terms of two copies of this Chern-Simons action. But importantly, the phase spaces of these two theories are different. They're not the same, and that's good because gravity, at least in this theory, is not equivalent to a gauge theory. There are more conceptual issues with this relationship. So for example, large diffeomorphisms are gauged in gravity. They're not in Chern-Simons theory or in gauge theory in general. And in gravity, we sum over topologies, whereas in TQFT, we usually consider on some fixed background manifold. Summing over topologies would be some very weird thing to do in TQFT. So let's discuss the canonical quantization of the theory. So consider the 3D gravity on some free manifold that locally looks like sigma, which is a Riemann surface, times R. So we think of this sigma surface, which I sketched here, as some initial value surface on which we want to do canonical quantization. So as I described previously, the phase space of the gauge theory is the moduli space of flat SL2R connections on sigma, on this initial value surface. But in fact, most of these connections, when translated to the gravitational variables, are really not good initial conditions for gravity. Most of them look very singular. So for example, you would have the flat connection A equals 0, which obviously is not good in gravity. You want the metric to be non-degenerate. The Vielbein should be invertible, that sort of thing. Now the gravity phase space, on the other hand, is in fact a proper subset of this Chern-Simons phase space. It's given by two copies of this space that I call curly T of sigma, which is the Teichmuller space of sigma. This is just the space of hyperbolic metrics on sigma. And it's a non-trivial theorem that you can uplift these hyperbolic metrics to smooth 3D metrics on this 3D manifold. So this is some proper subset. In fact, this Chern-Simons phase space is a disconnected space with a number of disconnected components. And this Teichmuller component is a particular component. So we'll quantize that. So in order to proceed to the quantum theory, we have to discuss the quantization of Teichmuller space. This sounds very formidable, but thankfully this was carried out in the 80s by Hermann Verlinde in a kind of amazing paper from 1989, a very prescient paper. So there, what he showed was that in this quantization of Teichmuller space, the Hilbert space, so that in these variables, the gravity Hilbert space is given by two copies of this curly H Hilbert space. H here is the space of Virasoro conformal blocks on this surface sigma. And that sounds scary. I'll try to unpack it a little bit. I just want to say that these conformal blocks are a very natural family of wave functions on this Teichmuller space. And in fact, it's quite intuitive from the point of view of holography, because the gravity partition function, after all, should be equivalent to a CFT partition function. And these conformal blocks that span this Hilbert space are the kinematic building blocks of CFT correlation functions on sigma. So from the point of view of holography, this is a very natural proposal. But perhaps unfamiliar, from the point of view of TQFT, this is an infinite dimensional Hilbert space, and that will lead to some subtleties. So let me just say a few more words about what conformal blocks are. So as I said earlier, they're these building blocks of CFT observables. So consider some correlation function of the CFT on some Riemann surface. The algorithm to compute it is to do a pair of pants decomposition of the surface sigma, insert a complete set of states on all of the internal cuffs, and then you get structure constants for each pair of pants. And so that leads to this decomposition where you sum over these complete set of states that you insert at the cuffs. You get structure constants or CFT data for each of those pairs of pants. And the remaining kinematic dependence of the observable is captured by these conformal blocks, which describe the exchange of this complete set of states. Or sorry, of one of these states that appears in this sum, along with its conformal family.
See, space of Virasoro conformal blocks infinite dimensional even on a sphere.
Yeah, because the complete set of states is a continuous space. This is unlike the case in the Chern-Simons WZW model of correspondence, where they're a discrete finite set of conformal blocks. So I'll call these conformal blocks curly F, and they're labeled by this parameter that I'll call P, which is just some convenient label for the quantum numbers of the exchange states and the internal pairs of pants. They also depend on the moduli of the Riemann surface and the locations of the punctures. I collectively denote those by N. But this P label will show up a bit in what follows. And so the pair of pants decomposition of this correlation function is far from unique. There are many different ways that you could imagine doing this. And the equivalence of these different pair of pants decompositions leads to an infinite set of non-perturbative constraints on the CFT data. And that's sometimes known as the conformal bootstrap. Okay, very good. Let's return to gravity. So a Hilbert space is more than a vector space. I've told you that it's this space of Virasoro blocks, but for it to really be thought of as a Hilbert space, we need to equip it with an inner product. And Hermann actually did this in his paper in 1989. Our main contribution was to give a sort of modern reinterpretation of his formula. So we seek some procedure that takes two conformal blocks and returns a number. Now, these conformal blocks are wave functions on this Teichmüller space, so a natural thing to do is to integrate them over Teichmüller space. And there's some measure here that I call mu, such that this integration is well defined. And in fact, the structure that appears in this inner product is very, very similar to that that you encounter in computing string diagrams in worldsheet perturbative string theory. The reason for that is that this Teichmüller space is locally equivalent to moduli space. So in CFT, we integrate in string theory, we integrate CFT correlation functions over moduli space. Here we're integrating individual conformal blocks, which are not themselves crossing invariant or modular invariant. So you have to integrate them over all of this Teichmüller space. But this perspective, in fact, led us to consider a very closely related string theory in 2D, and this goes under the name of the Virasoro minimal string.
Wait, that's sorry, I didn't understand.
Yeah.
Then if you have images which were related by some.
You could imagine summing the conformal blocks over images, but here I'm talking about the inner product of individual conformal blocks. So those are definitely not crossing invariant on their own.
Why don't you get an infinity if you integrate overall Teichmüller space? This isn't, the integrand isn't modular invariant.
That's right. Yeah, the integrand is not. If it were modular invariant, you would get an infinity from integrating overall of Teichmüller space.
Okay, and why isn't it integrand?
Just because these are individual conformal blocks. To get something crossing invariant, you have to sum over infinitely many conformal blocks with very finely tuned structure constants.
Oh, hey, can you remind me what P was?
Sorry, yeah. P, this is important. This label P is a label for the conformal weights of the internal states that you exchange. And it's real. This P parameter is real for states above the black hole threshold. And this will be, in a sense, a complete set of states. Okay, good. So that's the main thing I want to say here. There's some explicit form for the inner product. This mu, in fact, involves some correlation function of an auxiliary CFT with central charge that cancels the Weil anomaly. So the analogy with the string worldsheet diagrams is really quite precise. So up until now, you can interpret almost everything I've said as review. But a main contribution of our paper, in my view, was to explicitly evaluate this inner product. And what we showed is that this inner product is in fact orthogonal. So you take two conformal blocks with different sets of internal weights, labeled by these P parameters, and the inner product is delta function supported on P equals P prime, with some non-trivial measure, which I call rho sigma. And we know what this is. It's some known function. We argue for this in the paper from a variety of points of view. And so there's a small comment here about when is this inner product normalizable. It in fact requires these states to be above the C minus 1 over 24 threshold, so P real here. So conformal blocks that exchange some lighter operators in fact give a strictly infinite inner product.
It's the OPE density, that's the P prime.
Yeah, so you can, so similar to how you have a density of states that you infer from the torus partition function, for the, say, the sphere 4-point function in Liouville CFT, you get that by integrating conformal blocks against some OPE data as some function of P. So you integrate over P CFT data that depends on P times conformal blocks that depend on P.
That would have 3 indices.
It's all labeled by, it's some combination. So sigma here, it could be like a 4-punctured sphere, and it's all labeled by, so the external states are built into the label sigma, and you view it as some function only of the internal states that you exchange. It's very compact notation. It might have been useful to write some example formula. Okay, and a non-trivial thing about this conformal block Hilbert space. So I told you earlier that there are different pair of Pants decompositions one can consider. But it's a nice fact about these conformal blocks that they transform nicely under these change of pair of Pants decomposition. So you can take this block in what's called the T channel, 1,4 to 2,3, and express it in a complete basis of blocks in this dual S channel, 1,2 to 4,3. And notice that this the states that appear all have real P. So it's non-trivial that these normalizable blocks that are the blocks that are normalizable with respect to this inner product form a complete basis in this sense. So this crossing kernel object F that appears here is explicitly known and satisfies the Moore-Seiberg consistency conditions, which guarantees this invariance under different pair of Pants decomposition.
So is P real because of some unitarity argument?
P here is just the range that constitutes a complete basis under this change of pair of Pants decomposition. And it's the same set of blocks for which the inner product is normalizable. This is delta function. Yeah. So it's a non-trivial fact that this inner product I wrote down earlier is actually preserved under these crossing transformations. And you can actually view that as one way of deriving the form of the inner product. So the upshot is that the Hilbert space closes under these crossing transformations, and the quantization is independent of the choice of basis of blocks, as it should be. And what this means is that we have enough data to define a consistent TQFT. So let's summarize what we've done so far. We started with 2 copies of SL2R Chern-Simons theory in this canonical quantization. And we imposed what, from the gauge theory point of view, looks like a seemingly very arbitrary restriction on the phase space. So we picked out this Teichmuller component and decided we were only going to quantize that.
Nothing takes you out of that.
Yeah, exactly. That's the point. So we quantized this component, and this led us to this Virasoro TQFT, whose Hilbert space is the space of conformal blocks on these surfaces sigma. And so this defines it because of this property that it's preserved by crossing transformations. It's unitary inner product. This defines a consistent TQFT, despite some subtleties, maybe unfamiliar features that are associated with the fact that this Hilbert space is infinite dimensional.
What's the difference between the Virasoro TQFT and the Liouville CFT?
Well, one way to think about it is that the Hilbert space of this TQFT on sigma is spanned by the conformal blocks that appear in Liouville CFT.
So they have sort of the same data, right?
You can think about it, so if you know the Chern-Simons WZW model correspondence,
Yeah.
Liouville CFT is related to this theory in exactly the same way as the WZW model is related to the Chern-Simons theory. The Hilbert space is the space of blocks in the theory. There's some inner product.
And is this Liouville CFT the same as the one in the Sargent log vector, or is it?
Probably secretly, you could reinterpret their story in terms of this TQFT, but we haven't done that. Yeah. But I don't want to, just to clarify, I'm not saying that the dual of 3D gravity is Liouville CFT, but rather it's described by this TQFT.
It sounds.
You can compute the partition function on any surface or any hyperbolic 3 manifold, and it's true that in some cases the partition function agrees with that of Liouville CFT. In most situations, it doesn't.
Okay.
It's just like in the Chern-Simons WZW model. If you consider these Euclidean wormholes with 2 asymptotic boundaries,
Yeah.
the partition function is the WZW model partition function.
Yeah.
Maybe the way to say it is that the nature of the duality is different from ADS CFT in the Chern-Simons WZW model correspondence. Okay, so we're in the last part of the talk now. So now that we have this seemingly kind of formal structure, let's try to apply it. And so if you have a TQFT, its role in life is to compute for you partition functions on 3 manifolds in the 3D case. So the way we think about it is that if the boundary is some disjoint union of surfaces, then the TQFT partition function, which I call Z-vir, should be thought of as a vector in this tensor product Hilbert space that's associated with each of the asymptotic boundaries. So here's where we're going from Lorentzian to Euclidean signature. So now we interpret the Hilbert space as having to do with the asymptotic boundaries. So this partition function is some state in the Hilbert spaces associated with each of these boundaries. So in practice, we apply fairly standard TQFT methods. In particular, we apply surgery techniques. So what we do is we cut the configuration through the bulk, which divides it into 2 pieces, M1 and M2. In doing the cutting, you introduce some extra boundary that wasn't there before. So you compute the partition function on each of these smaller pieces, M1 and M2. One way to do that is to insert a complete set of states on all of the other boundaries, which produces some state in the Hilbert space of this cutting surface. And then the partition function is given by the inner product of these individual partition functions in this Hilbert space of the cutting surface. So there's a very general prescription that involves first surgery, cutting it into these 2 pieces along some surface in the bulk. You insert some complete set of states with respect to the outer or the other asymptotic boundaries, which gives you some state in the Hilbert space of this cutting surface, and then you take the inner product. So the main tool we use for this is known as Heegard splitting. It's simplest to describe for closed 3 manifolds without asymptotic boundaries, but it can be readily generalized to allow asymptotic boundaries and Wilson lines in the bulk. So it's a non-trivial fact that any 3 manifold can be decomposed into 2 what are called handle bodies, which I'll call S sigma. So what is a handle body? It's you take a Riemann surface sigma and you fill it in the bulk along some choice of cycles. So that gives you like the simplest example would be like a solid torus, or here I've drawn some solid genus 2 surface where you fill in the genus 2 surface. So you take 2 of these handle bodies, and then the boundaries of these handle bodies, which are the surface sigma, sometimes called the splitting surface, you identify them up to some modular transformation or crossing transformation on the boundaries.
Is this like a connected sum?
It's like that, but with some more complicated cutting surface. Yeah. Now the TQFT partition function on each handle body prepares some special state in the Hilbert space. It's just the identity block because there's nothing going on in the interior of these handle bodies. So then the TQFT partition function is just given by the expectation value of the representation of this mapping class group transformation, this modular transformation on this boundary Hilbert space. Now, the identity block actually isn't a normalizable state in this Hilbert space because it lives below this C/24 threshold. So if I take phi to be the identity, this inner product diverges. So heuristically, we expect this to be finite for phi, this modular transformation, to be whenever phi is sufficiently complicated. And we expect that it's finite whenever m is hyperbolic. So essentially, whenever phi is sufficiently complicated, m should be hyperbolic. Because after all, it's in those situations where m has ADS3 gravity emits a classical solution.
This is the vacuum state, is that the?
Yeah, where you insert the internal state is just the identity from a module. Okay, so that's the general picture. This TQFT partition function is defined on a fixed topology. Or as I told you at the beginning, the gravity path integral involves the sum over topologies. So there's also, one has to worry about this mapping class group, which is the space of large diffeomorphisms of M. I put out another label here for the boundary component just to emphasize that it should preserve the boundaries, which captures the mismatch between the gravity and TQFT gauge groups. So it should be gauged in the bulk. Now, there are also large diffeomorphisms that come from crossing transformations acting purely on the boundary. And these are captured by the mapping class group of the boundary components. And those should be also included in the sum over topologies. So the proposal for this like equivalence class of manifolds that are related by crossing transformations of the boundary is to compute the TQFT partition function on M, square it, because remember there are two copies of the TQFT in gravity, and then sum over these boundary mapping class group transformations, gauged out by the bulk mapping class group. So the conjecture, which holds up in all the examples we've studied, is that this partition function should be finite whenever M is hyperbolic. In other words, whenever it's a solution to the Einstein equations. So this sum over boundary mapping class group elements will take care of the modular invariance that Andy was referring to at the beginning. Okay, so let's work through a couple of examples explicitly and get our hands dirty, just to show that this thing is actually useful. So let's revisit this Euclidean wormhole that I described at the beginning, which captures the variance of the CFT observables in this Gaussian ensemble. Now, in TQFT, this Euclidean wormhole, where you take sigma times an interval, is a kind of trivial thing, because like, think about cutting open some other three manifold along the surface sigma. You can glue in the Euclidean wormhole and you haven't done anything topologically. So the way we think of the partition function of this Euclidean wormhole is like the resolution of the identity in this boundary Hilbert space. And indeed, you can compute it in this way and show that it agrees with this variance of the CFT partition function in the Gaussian ensemble. Whereas, as I mentioned on the last slide, the full gravity partition function also includes a sum over relative crossing transformations on the boundary. So the boundary mapping class group is just two copies of the mapping class group of sigma. And there's a bulk mapping class group that acts on both simultaneously. So you do the quotient I described on the previous slide, and you get this sum over relative crossing transformations, where you do you fix one of the boundaries and act with the other with a modular transformation. Now, I told you that this Gaussian ensemble on its own is incomplete. And in particular, for consistency of the whole story from the point of view of locality of the boundary theory, there must be non-Gaussian corrections. And the leading non-Gaussian correction in this ensemble of CFT data is controlled by this four boundary wormhole that I sketched here. So this has four boundaries, each of which is a three-punctured sphere, and it has defects propagating in the bulk in this sort of tetrahedral way. And this controls this fourth moment that sort of relates the S and T channels in the four-point function. Now, unlike the case of the Euclidean wormhole, where in some situations you could at least write down a metric, in this case, I know of no way to compute the action on this configuration in the metric formalism.
Maybe you said this already, but the red defects are just Wilson lines on that.
Yes, yeah, Wilson lines in the TQFT, exactly. That's right. But you can think of them as massive particles in the very massive particles in the ADS3 theory. But in the TQFT picture, although I have no clue how to compute this in the metric formalism, it just becomes a straightforward application of this inner product in the TQFT and of this Haggard splitting technology. So what I do is I cut through the wormhole in the bulk. You notice I'm cutting through some topology that's like a 4-punctured sphere. So it has 4 of these defects going through it. So I have the state on the left and the state on the right that I create by doing this cutting. And I take their inner product in this Hilbert space of the 4-punctured sphere. And I get the following very explicit formula. It's given in terms of this Virasoro 6J symbol, which is related to this crossing kernel I wrote earlier in a simple way. And intuitively, that makes sense because these states that I'm taking the inner product of are related to SNT channel sphere 4-point conformal blocks. So this is some very explicit formula for this 4-boundary wormhole partition function in terms of the CFT data of these, in terms of the conformal weights rather of these massive particles. Now this is also suggestive because it's known in the large C limit, the semi-classical limit, this 6J symbol, in fact, exponentiates to the volume of a particular hyperbolic tetrahedron with dihedral angles that are specified by these conformal weights. So that's very suggestive. Now you can go further and compute higher moments of the CFT data by looking at yet higher boundary wormholes. So here's an example of a 6-boundary wormhole, defects arranged in this sort of basketball-like configuration. The procedure is the exact same. You can cut it into 2 pieces. This time I'm just cutting along a 3-punctured sphere and take the inner product. And again, I get this product of 6J symbols, which controls this 6th moment in the CFT ensemble. This story generalizes. Here's a yet different 6-boundary wormhole that contributes to yet a different 6th moment of the CFT data and involves this integral over 3 6J symbols. And the reason I'm writing these down is because these results, although they involve this nasty object, the 6J symbol, they're rather simple when phrased in terms of the 6J symbol, and they suggest that there could be some very simple diagrammatic rules that compute the statistics of the CFT data. And moreover, it suggests a simplicial view of 3D gravity where, so there's this old story where you can triangulate the 3-manifold into tetrahedra in 3D, and then glue the tetrahedra together in some way. And then morally, because of this fact that the 6J symbol exponentiates to this volume of the tetrahedron, the volume just is inherited, the on-shell action is inherited from the volumes of the tetrahedra in this simplicial decomposition. So this suggests that there's yet a simpler way of formulating the theory. As a final example, maybe I won't go through the details here, but I just want to advertise it because I think it's kind of cool. You know, these partition functions compute topological invariance on 3 manifolds. So there's a very rich zoo of examples you could consider. In particular, you can consider knot complements, which are where you take a knot embedded in the 3 sphere, and then the complement of that knot is sometimes a hyperbolic 3 manifold. Now, the holographic interpretation of these things is totally unclear because there isn't an asymptotic boundary here, but I still think it's cool to study. So you can use the same splitting technique to evaluate the partition function, and you get this explicit thing, again, involving the 6J symbol. And interestingly, in the large C limit, you can evaluate this thing by saddle point, and it exponentiates to the hyperbolic volume of this figure-8 knot complement, which I think is kind of cool, but the interpretation in 3D gravity, particular for holography, is very unclear. All right, so let's wrap up. Today I've discussed a concrete proposal for ADS3 gravity in terms of a novel but well-defined topological quantum field theory that's defined by quantizing the Tegeler space. And this seems to give well-defined answers for the partition functions whenever the 3-manifold is hyperbolic. In other words, it admits a solution in 3D gravity. So yeah, the main thing is that this leads to an extremely concrete and explicit prescription to compute the partition functions using more or less standard TQFT techniques. And as we saw in these last few examples, it trivializes and simplifies many things that were either very hard in the metric formalism or just not possible. And it makes as I tried to emphasize at the end, it makes a bit more manifest the relation with this, the statistics of CFT data and this ensemble description of 3D gravity. So optimistically, one would hope that this technology should be useful in determining the sense in which any version of this pure theory makes sense at the quantum level. There are many future directions. In view of time, let me just leave them on screen and we can discuss afterwards. So thanks for your time.
Thank you, Scott. We have time for questions. Also, there is a question online.
Okay.
I will start. So Priya was asking, is the gluing straightforward for the Euclidean wormhole because it's unique?
Unique in which sense?
There are all these gluings.
Sorry, I don't mean to respond to them.
Priya, you want to ask
Yeah.
that?
Yeah, can you hear me?
Wait. Priya, can you hear us?
I can hear you. Can you hear me?
Yes.
Hi, thanks so much. Really interesting. So I was curious if these gluings are straightforward because there's only one way to glue them. It's unique.
Yeah, I suppose it's related to this fact I mentioned when I first introduced it, which is that it's, at least topologically, the Euclidean wormhole is a kind of trivial thing. It's like almost like a propagator, right? You can just cut open and glue it in and you haven't done anything. So it has to respect that property. And that essentially does fix the answer uniquely, given the inner product I described.
So that doesn't, the factorization problem that you mentioned is related to the pentagon.
Yeah.
So that does, so.
It doesn't solve that because I haven't told you, this problem with the sum over topologies is still totally present. And so, it doesn't provide any resolution for that, but it at least allows you to compute essentially any on-shelf solution in 3D gravity very explicitly. So that's sort of the next thing that one needs to understand, is to how to deal with that. I gave some partial prescription for the sum that involves the sum over boundary mapping class group, boundary modular transformations. But in some very simple examples that I alluded to at the beginning, like the solid torus, when the boundary is a torus, the sum has some pathologies. So it's not guaranteed to lead to a satisfying answer here. And certainly factorization does not seem likely to fall out of this procedure.
If the factorization is absent, does that signal some kind of anomaly in the bulk? DPO anomaly, because you're saying it should be DQFT. So
you can kill or you can fix the large diffeo anomaly, but still suffer from this factorization problem.
So the factorization doesn't just follow from it being a TQFT.
Yeah. There was an interesting story due to Benini and collaborators from a couple of years ago, where they considered these simple Chern-Simons like theories for gravity and showed that the bulk theory has some one-form global symmetry. And what they showed was that gauging that one-form global symmetry, this is non-unique. There are many ways to do it, but a given choice of gauging of that one-form global symmetry will project you to a specific rational CFT on the boundary. So one could imagine that there's something like that here, where there's
It's more global symmetry.
Well, that was partly the motivation for this work by Benini, was to get rid of the global symmetry by gauging.
Oh, that's what gauged it.
Yeah. There's probably some way of generalizing that story, but I don't think it would be very useful, because he would be saying that the gaugeability of this subset of the Wilson lines is just like equivalent to the crossing equation. So you have to solve the crossing equations to find this CFT. Andy, you had a question?
Yeah, so this local very short TQFT, it's not the whole gravitational usual orbit.
Yeah.
Could it be that there's some ordinary unitary CFT whose large n limit, whose dual to some bulk theory, whose large n limit was this
At the level of individual topologies?
Yeah, whose large n limit was it full graphic duals of some bulk theory in the usual sense?
Yeah.
And in a large n limit, you get this out.
Yeah, that would be the most optimistic thing.
That would be what you would hope.
Yeah, I
That
think
would
so.
be what you would.
Yeah, that there's really some large C family of theories and family of dualities that this theory captures the statistics of.
So somehow, so there's a slogan that both gravity is thermodynamics. But now this. Reverse articulation
Yeah.
is also thermodynamics.
Yeah, it's statistics of the CFT data more generally. I think is the way it captures these universal statistics of the structure constants of the space of chaotic solutions to the crossing equations. So that's how we think of it. But it doesn't tell us what the solutions are. But
if we found any unitary,
I would be happy with
if
that.
we found any unitary CFT larger than that was the
This book theory, yeah.
or the Liouville theory,
Yeah, sure.
then we could just define them all to be.
Well, if you had some theory of some large C family of solutions to the crossing equations with this gap and so on, then you wouldn't really need this thing, right? I mean, this provides a sort of coarse-grained description of the space of those theories, is the way I think about it.
So finding that is a very hard.
Yeah, exactly. This theory tells you about statistics in that space, but it doesn't tell you what the members are, like what the space of CFTs actually are. But you learn some coarse-grained property of those family of theories.
So I was trying to remind myself of the loop quantum gravity story.
Yeah.
So in that case, I guess you would sum up the whole phase space of the gauge theory in some way. So people have this Peter-Weil theorem to compute these volumes. How is that volume computation related to the Tech-Muller volumes?
I'm not very familiar with the loop quantum gravity story, but certainly the simplicial 3D gravity that I was sort of gesturing towards at the end is something that the loop quantum gravity people have thought about, but I'm not familiar with these Peter-Weil.
Because there are many inner products or Tech-Muller space. They use one. I think Peter some volume, Peter some.
Oh yeah, here in this, I think it should be the same because in this quantization, you have to specify a symplectic form, and the convenient choice is the Weber symplectic form.
I see. Oh,
So I think it should be related. Yeah.
Yes.
I have a clarificatory question from something you said way in the beginning, where one of the benefits of the Euclidean path integral may be that it allows us to retreat from string theory and discover the properties of a simpler pure quantum gravity formalism. But then you also said that it might also this endeavor might also prove that string theory is the only game in town. So can you just clarify?
Yeah.
Where that's coming from?
So if one could ultimately show that there's something like fundamentally inconsistent about this pure theory, I mean, there's this factorization problem and so on, but if one could really nail down what is wrong with it, then you might learn what you need to add to the theory to make it consistent. And it could be that the things you have to add to make the theory consistent ultimately lead you to string theory. It's a very optimistic reading, I think, of this program, but I think it's one of the points of trying to study these simpler theories to see if they're not consistent, what do you need to make it consistent?
Or it might lead you to a class of.
Yeah.
A bigger class of things, which M theories.
Sure,
right?
sure, yeah.
So it might lead you to some class of things.
That includes,
Yeah.
But at least we would have a better picture of what was needed. Whereas now we're kind of still grasping around a bit. Dark.
So just to clarify, the factorization problem is a problem for the holographic interpretation, not a problem for the gravitational theory itself. Is that?
I mean, on its own merits, yeah, it's a problem for the interpretation of the quantum mechanical boundary theory.
Yeah.
It means that the boundary theory doesn't really obey quantum mechanics in the usual sense.
So it doesn't signal any anomalies in the bulk theory. or any.
But then I don't,
things.
but then, absent holography, if you give up on holography in the usual sense and you're not doing string theory, then determining what the principles of UV complete quantum gravity should be, it seems like you're also grasping around.
But can it be a pathology of Euclidean?
Perturbative Euclidean, like in the,
No, pathology, like, it may be that it doesn't, this problem doesn't exist in Valencia.
well,
Because sometimes in Euclidean signature, we have more configurations, right? The deterministic conditions.
yeah. But I still think you should be able to do holography in Euclidean signature, like, like these black hole thermodynamics, for example, you can access from Euclidean gravity.
Okay, I think it's time to conclude. Let's thank our speaker again.